Okay, in this presentation we're going to look at a normal random variable question, a normal probability distribution. So my cycle journey to work is 3 kilometers and my cycling time in minutes, if there are no delays, is normally distributed with a mean of 15 and a variance of 1. Watch out for the variance there, okay? Variance is equal to 1, okay? So find the probability that if there are no delays, I get to work in at most 17 minutes. Now watch out for the wording here. At most means that 17 minutes or less, particularly if English is not your first language. Okay, so let x represent cycling time without delays. X is normally distributed with mean of 15, mu is equal to 15, and variance equal to 1. Okay, remember you always put in the variance there, so that's 1, the variance 1, not the standard deviation 1. I'll come to that in a second. And the question asks us, compute the probability that x is less than or equal to 17, okay, does not exceed 17 minutes. So the z-score is the first thing we do, okay? So the z-score for 17 minutes is 17 minus mu over sigma, and here sigma is the standard deviation. So that is 17 minus 15 over 1. Remember, the square root of 1 is 1, so if the variance is 1, the standard deviation is 1. So we have 2 divided by 1, and that is 2. I'm going to write that to 2 decimal places because that's sort of what fits with the statistical tables shortly. So I always write a z-score 2 decimal places, even if it's not absolutely necessary, just to be consistent. So the question asks us the probability of x less than or equal to 17. That is equal to the probability of z or z being less than or equal to 2. Now I'm going to use this function here called the phi function, which is a cumulative distribution function of the standard normal distribution. Okay, so I have this symbol here, phi. Okay, there I have it. And that means that's essentially the same as this. Okay. So what we do is we use statistical tables to look up that number. I'm not going to do that now, but if you do, you should get an answer of 0.9772. That there. Okay. So we're going to move on to the next part here. So in the last question, I talked about delays or lack of delays. Now this is what I meant here. So let's look at part B. Part B, on my route home, on my route, there are 3 sets of traffic lights. Each time I meet a traffic light, I'm delayed by a random time that is normally distributed with a mean of 0.7 and a variance of 0.09. Okay. These lights operate independently. Find the probability of my getting to work in at most 17 minutes. So it's very similar to the same question this is the question we've just done previously, but we're just sort of elaborating a little bit or making it a bit more difficult. So there's 3 scenarios. One is if one light is set at red when I reach it, so I'm going to be delayed for a while. So if just 2 sets of lights are red if I reach them, okay, so I could get delayed twice by 2 red lights. And finally, if 3 red lights are delaying me, so if all 3 lights are set to red when I reach them. So it's 3 different questions, but more or less it's the same idea between each of the 3 of them there. Okay, so essentially what we're going to do here is we have to add in our delay times, and they're also normally distributed. So essentially what we're doing is adding one normally distributed random variable to another. So in the first instance, t is the total time for each in the 3 scenarios. So we're treating the 3 scenarios separately. So if I get delayed at 1 red light, the total duration of my trip is the 15 minutes for the trip plus the 0.7 minutes for the delay. So altogether, I expect, if I get delayed, my journey time to be 15.7 minutes. And the variance, essentially what we do here is when we are combining 2 normal random variables, essentially what we do is just simply add the variance. So 1 plus 0.9, 1 from the previous question, plus 0.9 for 1 red light. So what we have here is probability of t less than or equal to 17 minutes. We approach it the same way. Here the variance is 1.09. So this turns into a standard deviation, which is the square root of 1.09. And that works out to be I'm missing an equal sign there. 1.0440. And also what we have there is the mean is 15.7. So 17 minus 15.7, that is 1.3. 1.3 divided by 1.044. Our z-score, so to speak, is over here. This is our z-score here, and that is 1.245. We get the cumulative distribution function for that, phi, and we look at that in the statistical tables. Now, I said that I was going to use 2 decimal places. I've already made a liar of myself, but that's you can get as close as you can to that. So it might be 1.24 or 1.25. Anyway, your answer should be around 0.8934. So 2 red lights, and another typo that drives me nuts. 2 red lights is the same scenario again. We're adding 3 normally distributed random variables the exact same way as we've done before. Add the means, add the variances. 15 plus 0.7 plus 0.7, and the variances are 1 plus 0.09 and 0.09. That is 16.4 as our mean and 1.18 is our variance. So it's exactly approaching it the same way as we've done before. So our z-score is 17 minus 16.4 divided by the square root of 1.18. Just to be clear, I am here now. Okay. And when we work that out, we get 0.6 divided by 1.0863. And our cumulative distribution function there is, when we work that out from our statistical tables, 0.55 should get us close enough to our answer from the tables, which is 0.7096. And likewise, the last one there, it is just almost the same. Just actually, you have to be a little bit careful here. We'll get a negative z-score minus 0.0887, which is, if you're looking at it from statistical tables, would be a tricky 1.09. Use the symmetry rule to figure that out. I'm not going to get into that here, but essentially that is how we would approach it there. So using the symmetry rule to find that value there, for the probability for that value there, and it should work out to be 0.4646. Close enough to that. Okay, so if you're not familiar with the complement rule and the symmetry rule for the normal distribution, I suggest you have a look at that before you continue. Moving on to part C, suppose that for each set of lights the chance of delay is 0.5. That means the chance of a red light is 0.5, 50-50. Deduce the mean time for my total journey time is, the expected mean time is 16.05 minutes. Okay, so it's essentially find the expected value of t. So this is using the normal distribution, but also we are using the binomial distribution here. So that's important here. So this sets up a bit of a clue. So what we're dealing with here is the binomial distribution. Okay, my pen is not great today. Okay, so what we have there is n, which is 3 traffic lights, and p, the probability of them being red. So the number of delays, the number of red lights, is distributed as binomial with n equal to 3 and p is equal to 1/2, 1 over 2. Now, so essentially, this is a very simple scenario. So what I'm going to do for the binomial distribution, so essentially what I'm going to do here is just, for the sake of brevity, give the probability of each of the 3 scenarios. So no delays is 1/8, 1 over 8. 1 red light, either the first or the second or the third, one of them goes red, is 3 over 8. 2 red lights is also 3 over 8, and finally, that you get all 3 red lights, the probability of that is 1/8. So what we have here now is extending it out a bit further. What we have here is a discrete random variable. So the expected time and the probability of that scenario. So each of the scenarios, no delays, 1 red light, 2 red lights, 3 red lights, they are described by durations. The expected time, 15, 15.7, 16.4, and 17.1. Okay, and so each has a probability which I've just described there. So the expected time, now this is a little bit confusing. This is the expected time in general, which combines all four scenarios. So some days you get no delays, some days you get one red light. So this is unconditional. Now these are expected times also. I probably should have used a slightly different phrase there, but this is conditional on the fact that there's no delays. This is conditional on the fact that there's one red light, and so on. So the unconditional mean of the total journey time is essentially a discrete random variable. We multiply x by the probability of x and add them all up. So 1 over 8 times 15 plus 3 over 8 times 15.7 plus 3 over 8 times 16.4 plus 1 over 8 times 17.1. Tot them all up, we get 128.4 divided by 8, which is 16.05 minutes. Okay, this is the last part here. So we expect our journey time to be 16.05 minutes, and we don't know how many red lights we're going to run into. Okay, so the variance of that random variable, the unconditional, when we don't know how many red lights we're going to look at or bump into, the variance of that is 1.5025. So given that that is the variance, use a suitable approximation to calculate the probability that over 10 journeys, my average journey time to work is at most 17 minutes. So essentially this is a sampling distribution question. This is the variance of an average, okay, given that the variance of the underlying variable is 1.5025. So this is essentially what we have here. This is a sampling error here, okay, which is the variance divided by n. Here is the number of trials or the sample size, okay, the standard error. So the mean time is normally distributed with a mean of 16.05 and a variance of 0.15025. Okay, so that is our variance. What we need is the square root of that. Okay, and the square root of that seems to be, using our calculator, 0.3876. So our z-score works out to be 2.451 or 2.45, and when we look that up in our tables, we should get a number close to 0.9929. Now just remember, actually, I keep talking about statistical tables, but you could look that up using statistical software as well, or something like that, Excel, just to check those numbers. So that's all 4 parts done. We'll leave it there. That's a good day's work.